Welcome to this podcast episode dedicated to the fascinating world of electrochemistry. Today, we will be taking a deep dive into some of the most important concepts for NET aspirants, breaking down complex ideas into easily understandable pieces and providing you with some tips to remember key concepts. Let's get started. Our first section begins with the idea that chemical reactions can produce electrical energy, and likewise, electrical energy can be used to carry out chemical reactions that don't happen spontaneously. This exciting field of study is called electrochemistry. It's not just about theory, but it also has many practical applications. From the production of metals, sodium hydroxide, chlorine, fluorine, and many other chemicals, to the creation of batteries and fuel cells, electrochemical methods are widely used. The advantage? These reactions can be energy efficient and less polluting, making electrochemistry a central player in creating eco-friendly technologies. But electrochemistry isn't just about the inanimate world. It also plays a crucial role in our bodies. The transmission of sensory signals through cells to the brain and back, and communication between cells, have an electrochemical origin. You may remember from Class 11, Unit 8, the concept of the Daniell cell. This cell is a perfect example of electrochemistry in action. It converts chemical energy into electrical energy during a redox reaction. To jog your memory, let's recall the structure of the Daniell cell. It consists of zinc and copper electrodes dipping into solutions of their respective salts. Remember this equation, Zns plus Cu2 plus, Ag, turns into Zn2 plus, Ag, plus Cus. This redox reaction converts chemical energy to electrical energy, giving an electrical potential of 1.1 V when the concentration of Zn2 plus and Cu2 plus ions is unity. Now, let's imagine applying an external potential to this system. As we increase this potential slowly, we see that the reaction continues until the opposing voltage reaches 1.1 V. At this point, the reaction stops, and no current flows through the cell. If we further increase the external potential, the reaction restarts, but in the opposite direction. The cell now acts as an electrolytic cell, utilizing electrical energy to drive non-spontaneous chemical reactions. To better understand this, let's break down the redox reaction in the Daniell cell into two half reactions. The reduction half reaction is Cu2 to E turning into Cus, and the oxidation half reaction is Zn turning into Zn2 to E. The reduction happens on the copper electrode, and the oxidation happens on the zinc electrode. This concept is crucial, and here is a tip to remember it. Think of ROX. Reduction occurs at the X, copper electrode. This will help you remember where each part of the reaction takes place. Remember, we can construct countless galvanic cells like the Daniell cell by combining different half cells. Each half cell consists of a metallic electrode dipped into an electrolyte, and the two half cells are connected both externally through a wire and internally through a salt bridge. To sum up this section, always remember the central role of electrochemistry in both theoretical and practical applications. The Daniell cell is a perfect example of how chemical reactions can be converted into electrical energy and vice versa. And finally, keep in mind the ROX tip to remember where each part of the reaction happens. As we begin, remember, the potential of an individual half cell cannot be measured directly. We can only measure the difference between the potentials of two half cells, which is essentially the EMF, electromotive force, of the cell. At the interface between an electrode and an electrolyte, there is a delicate equilibrium. Metal ions from the solution aim to deposit on the electrode, while metal atoms of the electrode aspire to enter the solution as ions. This tug-of-war results in a separation of charges, leading to the development of what we call the electrode potential. Now, when all species involved in a half cell have a concentration of unity, we refer to the resulting electrode potential as the standard electrode potential. A key point to remember here, according to UPAC convention, standard reduction potentials are now termed as standard electrode potentials. In a galvanic cell, the half cell where oxidation transpires is called the anode and it has a negative potential, while the half cell where reduction occurs is termed the cathode and it has a positive potential. When the switch is on, electrons flow from the negative electrode, anode, to the positive electrode, cathode, and the direction of current flow is opposite to that of electron flow. The potential difference between the two electrodes of a galvanic cell is known as the cell potential, measured in volts. It's the difference between the electrode potentials, reduction potentials, of the cathode and anode. This cell potential is also known as the cell EMF when no current is drawing through the cell. To remember this, think of cell potential as the power of disagreement or difference between the cathode and anode. When representing a galvanic cell, we usually place the anode on the left and the cathode on the right. The cell EMF is then given by the potential of the half cell on the right minus the potential of the half cell on the left, i.e., SL is equal to A right, A left. Now, let's introduce the standard hydrogen electrode, She. Its potential is zero at all temperatures. This electrode is made of platinum coated with platinum black, dipped in an acidic solution, and pure hydrogen gas is bubbled through it. The pressure of hydrogen gas is 1 bar, and the concentration of hydrogen ions in the solution is 1 molar. The standard hydrogen electrode is particularly useful as a reference half cell. When we construct a cell with the She as the anode and another half cell as the cathode, the cell potential equals the standard electrode potential of the given half cell. Let's look at a few examples. For the cell constructed with the She and a half cell consisting of Cu2 plus ions and copper, the cell EMF is 0.34 V. This value is the standard electrode potential for the half cell reaction Cu2 plus to ECU. Similarly, for the cell constructed with the She and a half cell consisting of Zn2 plus ions and zinc, the cell EMF is minus 0.76 V. This value is the standard electrode potential for the half cell reaction Zn2 plus to EZn. The values of these standard electrode potentials offer us a wealth of information. If the standard electrode potential of an electrode is positive, its reduced form is more stable than hydrogen gas. If it's negative, hydrogen gas is more stable than the reduced form of the species. For instance, the standard electrode potential for fluorine is the highest, indicating that fluorine gas has the maximum tendency to get reduced to fluoride ions and is the strongest oxidizing agent. On the other hand, lithium has the lowest electrode potential, which means that lithium metal is the most powerful reducing agent in an aqueous solution. In summary, the concepts of electrode potential, standard electrode potential, and the standard hydrogen electrode are central to understanding electrochemical reactions. They allow us to compare the relative reactivities and stability of different redox couples and predict the direction of redox reactions. So, keep these concepts at your fingertips as you prepare for your NEET exam. In this section, we will look at the Nernst equation, the relationship between cell potential and Gibbs energy of the reaction, and the concept of conductivity in electrolytic solutions. Starting with the Nernst equation, which is a powerful tool in electrochemistry. It states that the electrode potential at any concentration, when measured with respect to the standard hydrogen electrode, can be represented by a formula that includes the natural logarithm of the ion concentration. The equation for a general reaction is E is equal to E degree RT NF ln Q, where E is the electrode potential, E degree is the standard electrode potential, R is the gas constant, T is the temperature, N is the number of moles of electrons, F is the Faraday constant, and Q is the reaction quotient. Remember, this equation relates the electrode potential to the concentrations of the chemical species involved. For example, in a Daniell cell, the cell potential depends on the concentrations of Cu2 plus and Zn2 plus ions. As the concentration of Cu2 plus ions increases and as the concentration of Zn2 plus ions decreases, the cell potential increases. This is an important concept to remember. The cell potential is not a fixed value, but it varies depending on the ion concentrations. Next, the relationship between the cell potential and the Gibbs energy of the reaction is encapsulated in the equation ΔG is equal to NFE. Here, ΔG is the change in the Gibbs energy, N is the number of moles of electrons transferred in the reaction, F is the Faraday constant, and E is the cell potential. This equation is crucial in thermodynamics and electrochemistry as it connects the spontaneity of a reaction, Gibbs energy, with its electrical work output, cell potential. Lastly, the concept of conductivity is central in the study of electrochemistry. Conductivity, denoted by the Greek letter kappa, is the measure of a material's ability to conduct electric current. It's the reciprocal of resistivity. The conductivity of a solution depends on the nature of the electrolyte, the size and solvation of the ions, the viscosity of the solvent, the concentration of the electrolyte, and the temperature. When an electrolyte is dissolved in water, it provides its own ions, thereby increasing the solution's conductivity. Materials are classified into conductors, insulators, and semiconductors based on their conductivity. Metals and their alloys, for example, exhibit high conductivity and are thus known as conductors. Substances like glass and ceramics have very low conductivity and are known as insulators. Substances like silicon, which have conductivity values between those of conductors and insulators, are called semiconductors. These are the key concepts and equations covered in this section. They form the foundation for understanding the behavior of electrochemical cells and the movement of charge in electrolytic solutions. Firstly, we must comprehend the means by which we measure the conductivity of ionic solutions. The resistance of an ionic solution is measured using a specially designed vessel known as a conductivity cell. This cell essentially consists of two platinum electrodes coated with platinum black of equal area of cross-section A and separated by a certain distance L. The resistance R of the solution column confined between these electrodes is given by the equation R is equal to ρ, La, where ρ is the resistivity of the solution. The quantity La is termed the cell constant, represented by the symbol G star. Here is an essential point to remember. The cell constant G asterisk depends on the distance between the electrodes and their area of cross-section. It is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known, such as a KCl solution. Once the cell constant is determined, it can be used to measure the resistance or conductivity of any solution. The conductivity, kappa, of the solution is given by the equation kappa is equal to G asterisk R, which is the cell constant divided by the resistance of the solution. Now, let's focus on molar conductivity, denoted by the Greek letter lambda. Molar conductivity is the conductivity of an electrolyte solution divided by the molar concentration of the electrolyte, and so it's given by the equation lambda is equal to kappa C. The units of molar conductivity are Sm to mol 1 or Scm to mol 1, depending on whether you use Sm1 or Scm1 for conductivity, and mol M3 or mol L1 for concentration, respectively. It's important to understand that both conductivity and molar conductivity are affected by the concentration of the electrolyte in the solution. As the concentration decreases, conductivity also decreases for both weak and strong electrolytes. This is because the number of ions per unit volume, which carry the current in a solution, decreases upon dilution. However, molar conductivity is a more meaningful measure of a solution's ability to conduct electric current, as it takes into account the concentration of the electrolyte. It allows us to compare the conductivities of different electrolytes in a more standardized manner. In the next section, we will continue to discuss how conductivity and molar conductivity vary with concentration and delve deeper into the factors influencing this. Stay tuned. In this section, we will discuss the variation of conductivity and molar conductivity with concentration, dive into the Kohlrausch law of independent migration of ions, and see how these concepts are applied in practice. The conductivity of a solution, represented by the Greek letter kappa, measures its ability to conduct electric current. The conductivity of a solution can be determined using a conductivity cell, which measures the resistance of the solution. The ratio of the cell's dimensions, distance between the electrodes divided by their area of cross-section, is known as the cell constant, G**. Molar conductivity, represented by the Greek letter lambda, is a measure of a solution's conductivity per unit concentration. It is defined as the conductance of a volume V of solution that contains 1 mole of electrolyte, held between two electrodes of unit area and unit distance apart. Mathematically, molar conductivity is given by lambda is equal to kappa C, where C is the concentration of the electrolyte. As the concentration of the electrolyte decreases, the molar conductivity increases. This is because the total volume of solution that contains 1 mole of electrolyte increases with dilution. For strong electrolytes, molar conductivity increases slowly with dilution and can be described by the equation lambda is equal to lambda degree MAC, where lambda degree M is the limiting molar conductivity at infinite dilution, C is the concentration, and A is a constant. This equation implies that a plot of molar conductivity versus the square root of concentration will yield a straight line, the intercept of which gives lambda degree M and the slope of which gives A. The Kohlrausch law of independent migration of ions states that the limiting molar conductivity of an electrolyte is the sum of the limiting molar conductivities of its constituent ions. That is, lambda degree M is equal to V plus lambda degree plus V, lambda degree, where lambda degree plus and lambda degree are the limiting molar conductivities of the cation and anion, respectively, and V plus and V are the numbers of cations and anions per formula unit of the electrolyte. For weak electrolytes, the change in molar conductivity with dilution is more pronounced due to an increase in the degree of dissociation with dilution. At any given concentration, the degree of dissociation alpha can be approximated as alpha is equal to lambda and lambda degree M. The Kohlrausch law has several practical applications. It allows us to calculate the limiting molar conductivity of any electrolyte given the limiting molar conductivities of its individual ions. For weak electrolytes, the Kohlrausch law allows us to calculate the dissociation constant if we know the limiting molar conductivity and molar conductivity at a given concentration. In conclusion, understanding the concepts of conductivity and molar conductivity, the Kohlrausch law, and how they relate to each other is crucial in the field of electrochemistry. These concepts allow us to better understand the behavior of ions in solution and provide valuable insights into the properties of electrolytes. In this section, we will delve into the quantitative aspects of electrolysis, Faraday's laws of electrolysis, and the idea of primary batteries. Electrolysis refers to the process by which electrical energy is used to provoke a non-spontaneous chemical reaction. The cell that accomplishes this is called an electrolytic cell. The laws of electrolysis, formulated by Michael Faraday, delineate the quantitative aspects of electrolysis. 1. Faraday's first law of electrolysis states that the amount of chemical reaction at any electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. 2. Faraday's second law of electrolysis posits that the amounts of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. The unit of electricity or charge is the coulomb. Faraday found that 1 mole of electrons carries a charge of approximately 96,487 coulombs, a quantity known as Faraday's constant, F. The product of current, I in amperes, and time, T in seconds, gives the total charge, Q in coulombs, passed through the cell, given by Q is equal to it. For example, in commercial production of metals, very high current levels are used, amounting to about 0.518 F per second. Applying these laws, we can calculate the mass of a substance deposited at an electrode during electrolysis, or the volume of gas produced, by knowing the quantity of electricity passed and the stoichiometry of the reaction occurring at the electrode. Next, let's explore primary batteries. These are batteries in which the electrochemical reaction occurs only once, and they can't be reused after they're discharged. Examples include the dry cell, or Leckland cell, and the mercury cell. The dry cell is commonly used in devices like clocks and transistors. It consists of a zinc container acting as the anode, and a carbon rod surrounded by powdered manganese dioxide and carbon as the cathode. The space between the electrodes is filled with a moist paste of ammonium chloride, NH4Cl, and zinc chloride, ZnCl2. The cell has a potential of nearly 1.5 V. The mercury cell, suitable for low-current devices like hearing aids and watches, consists of a zinc-mercury amalgam as the anode and a paste of HGO and carbon as the cathode. The electrolyte is a paste of KOH and ZNO. In the next section, we will delve into secondary batteries and fuel cells. Stay tuned. In this section, we will delve into the concept of secondary batteries, the process of corrosion, and the role of electrochemistry in the development of alternative energy sources. Secondary batteries are batteries that can be recharged and reused. Unlike primary batteries, which can only undergo one round of chemical reactions, secondary batteries can undergo multiple cycles of charge and discharge. Examples of secondary batteries include lead storage batteries and nickel-cadmium batteries. The lead storage battery, also known as a lead-acid battery, is commonly used in automobiles and inverters. It consists of a lead anode and a grid of lead dioxide, PbO2, as the cathode, with a 38% solution of sulfuric acid used as the electrolyte. During the discharge cycle, Pb and PbO2 react with H2SO4 to form PbSO4 and water. During the charging cycle, this reaction is reversed. The nickel-cadmium cell, although more expensive to manufacture, has a longer lifespan than the lead storage battery. Here, the overall reaction during discharge is Cd plus to Ni, O to CdO plus to Ni, O plus H2O. Next, let's talk about corrosion. Corrosion happens when metals react with substances in their environment and get gradually eaten away. Corrosion of iron, or rusting, is a common example. It involves the oxidation of iron in the presence of water and air, forming hydrated iron, 3-oxide, also known as rust. Corrosion can cause significant damage to metal structures over time. Therefore, preventing corrosion, for instance by painting metal surfaces or by attaching a sacrificial anode, is an important aspect of maintaining metal objects and structures. Lastly, let's discuss fuel cells. Fuel cells are a type of electrochemical cell that directly converts the chemical energy of a fuel and an oxidizing agent into electricity. The most successful fuel cells use the reaction of hydrogen with oxygen to form water. Fuel cells are efficient and non-polluting, making them an attractive technology for the future. They have been used in experimental automobiles and were also used to provide electrical power in the Apollo space program. In the next section, we will continue to explore electrochemistry and its applications. Stay tuned. In this section, we will delve into secondary batteries, the process of corrosion, and the role of electrochemistry in the development of alternative energy sources. Secondary batteries, unlike primary batteries, can be recharged and reused. This makes them a more sustainable option for many applications. Two of the most commonly used secondary batteries are the lead storage battery and the nickel-cadmium battery. The lead storage battery, also known as the lead-acid battery, is often used in vehicles and inverters. It consists of a lead anode and a lead dioxide (PbO2) cathode. The electrolyte is a concentrated sulfuric acid solution. When the battery discharges, both the anode and cathode react with the sulfuric acid to produce lead sulfate and water. During recharging, the lead sulfate is converted back into lead and lead dioxide, and the water is converted back into sulfuric acid. The nickel-cadmium battery has a longer lifespan than the lead storage battery but is more expensive to manufacture. The overall reaction during its discharge is Cd plus to Ne, O to CdO plus to Ne, O plus H2O. Moving on to corrosion, which is an electrochemical process where metals react with their environment and degrade over time. The most common form of corrosion is the rusting of iron. When iron comes into contact with water in the presence of oxygen, it forms hydrated iron, oxide, or rust. Corrosion causes significant economic loss and can also lead to catastrophic structural failures. Various methods, such as painting, galvanizing, or using sacrificial anodes, are used to prevent corrosion. Fuel cells are a promising technology for the future of energy. They are electrochemical cells that convert the chemical energy of a fuel directly into electrical energy. The most common type of fuel cell uses hydrogen as the fuel and oxygen as the oxidizer. The only byproduct of this reaction is water, making fuel cells a clean source of energy. In the context of the hydrogen economy, the importance of electrochemical principles becomes clear. The production of hydrogen via electrolysis of water and its use in fuel cells are both electrochemical processes. As we move towards sustainable and non-polluting sources of energy, electrochemical technologies like these will play a pivotal role. In the next section, we will explore more practical applications of electrochemistry, from calculating the amount of product formed during electrolysis to predicting feasible redox reactions. Stay tuned. In this exploration of electrochemistry, we have delved into a wide array of topics such as galvanic and electrolytic cells, cell potentials, the Nernst equation, molar conductivity, Faraday's laws of electrolysis, primary and secondary batteries, corrosion, and fuel cells. We started by understanding the fundamentals of electrochemical cells, where chemical energy is converted into electrical energy in galvanic cells, and electrical energy is used to drive non-spontaneous reactions in electrolytic cells. We explored the Nernst equation, which allows us to calculate cell potentials at any concentrations, not just standard conditions. We then delved into the concept of molar conductivity and how it varies with concentration, leading us to Paul Roche's law of independent migration of ions, which has many practical applications. We also discussed Faraday's laws of electrolysis, which enable us to calculate the amount of substance deposited or liberated during electrolysis. Looking at applications of electrochemistry in everyday life, we discussed the functioning of primary and secondary batteries, as well as the importance of preventing corrosion, an electrochemical process that leads to the degradation of metals. We also touched upon the significance of fuel cells, which offer a clean and efficient method of energy conversion. In conclusion, electrochemistry plays a pivotal role in many areas of science and technology. From powering the electronic devices we use daily to providing insights for developing alternative energy sources, the principles of electrochemistry are deeply integrated into our technological advancements. Innovation in this field continues to drive progress, making our lives more convenient, sustainable, and environmentally friendly.